Good afternoon, everybody. My name is Yogendra, and I have my colleague Graham with me. We are from Impression Technologies, and we work on a patented process called hot forming and quenching, HFQ, which was invented at University of Birmingham and later industrialized at Imperial College London. So I may be speaking to some of the next inventors who could be coming up with some really nice processes and spin-offs. So far we have looked into tribology of what happens inside cars, let's say powertrains and engines. And we just wanted to give you an exposure to sheet metal forming and tribology in this field, particularly high temperature, which was researched in the UK a couple of decades ago, but slowly and steadily the focus has been shifted to EVs, and I don't blame anybody for that. So the objective is to introduce the process that has been patented and that we work on. It's tribology, not only in aluminium, but let's say touching on hot stamping of steels, and probably give you the challenges that we face and that we have surpassed. So we have done a lot, but a lot more needs to be done. So treat this as opportunities to get involved in sheet metal forming tribology. So we will just give the introduction about the company and the process. Then we'll look at tribosystems in HFQ, which is our patented process. Then I'll share some challenges that we are facing at the moment. And then Graham will pitch in and then talk about solutions. And then we'll just give you a brief summary and open to any questions and discussions. So we have been talking about automotive tribology. So a car has around 250 formed panels. That includes what we see outside, as in bodies, doors, hoods, inners, fenders, plus the components that go on to make the chassis. And more recently, there have been a lot of discussion on how to make chassis for electric vehicles, which is a completely different game altogether. On an average, there are 85 million cars produced every year. And like Ian mentioned on Josh's report, that friction can account up to 20% of the quality issues. And the number is roughly the same in automotive stampings, but more so, let's say, towards 20 when it comes to this novel processes such as hot form components. So I'm just giving you a glimpse of the inside of a car. And the parts in blue and red are hot formed, meaning that they don't happen at room temperature. The forming happens at elevated temperature. And it gives tremendous advantages for lightweighting, so reducing the weight of the car because batteries are heavier than engines. And secondly, it also makes the car safer for passengers because it gives you a much better crashworthiness because you can use more high strength and advanced alloys. So as we are moving towards a much more advanced processes, tribology becomes more important, and reducing the friction accounted losses in terms of scrap is also more important, more so in terms of sustainability, in reducing less material. There is no point in lightweighting and then using more in scrap. So this is the patented process that we call HFQ, or hot forming and end-die quenching. So it starts from left to right. So there are blanks cut to shape. Then the blanks go into a furnace where they are solution heat treated, which is solution heat treatment for aluminium, and it could be austenizing for steels. Then the blanks are rapidly transferred to a cooled die. So there's a male and a female cavity. And then the press comes down, it forms the part. At the end of forming, there is a dwell of few seconds to suck the heat out so that the part comes out at room temperature. Then the parts are cleaned, and then it goes into an aging oven where we get final properties. And here I've just shown two examples of if I were to form this part in cold using high strength aluminium, it splits into two. But if I do it hot through our process, we can make a very good part without any defects such as thinning or wrinkles. So here I just want to show you the process in action. And this is in our site in Germany. This is where the blank is taken into the furnace for solution heat treatment. And the component being formed is a door ring. So that's where the door is latched onto. Now it's out of the furnace and going inside the press in dies, and it's being formed. And after the quench time, it's removed from the press, visually inspected. And then it's stacked. That goes on for cleaning. Once it gets into the aging, where it gets the final property, so it's moving inside an aging oven. So that's the advantage of HFQ, is you can tailor the final properties of the part depending on where it sits and what are the mechanical property requirements. And now it goes for laser cutting to the final shape. That's now cut and stacked. And this is how we measure. So this is where all the quality issues on dimensional conformance, thinning are being measured and captured. Hopefully that gave you the idea of what the process is. So as a company, we only focus on ultra-high strength aluminum alloys through our patented process called HFQ. So far, we have invested 35 million in developing the technology. And at the moment, it's being used in companies like Aston Martin, Lucid in the US, and Lotus. We have been commercially producing parts since 2016. So there are around 39 different parts being produced as we speak, and an annual production volume of more than 250,000 parts. And in terms of our interactions with global OEMs, we are working with almost every single OEM in aerospace and automotive you can imagine. And we are based in Coventry, which is the automotive hub of the UK. And we operate from our technology headquarters in Coventry. So let's get into the interesting bit now. So let's talk about the Tribo system when it comes to sheet metal forming and especially HFQ. So there's a hot blank in between, and then the upper and lower tool, which are going to form the part. In HFQ, we spray lubricant on the tool, so the blank does not come with any lubricant. And then the tools could be of tool steels, cast iron, or any other ferrous materials, which are also can be coated with PVD coatings. And then there are a plethora of operating variables depending on what type of motion, type of blank, process parameters such as forming forces, sliding distances, relative velocity. More importantly, the temperature of the die and the part. And both the blank and the die comes with a certain surface finish. And then finally, the viscosity of the lubricant. So there are quite a few operating parameters that influence the Tribo system. And the tribometric output, essentially, what we all measure in tribology across the different fields, is coefficient of friction and wear. But the friction coefficient is a function of the friction force, which is in turn a function of asperative flattening, adhesion, and shearing. Because we are looking at a high temperature contact, there's oxidation both on the steel of the lubricant and on the aluminum blank. And there's also some dynamic effect to lubricants, such as squeezing out of the contact. And all these aspects together influence the contact conditions. And after we start pressing one part to the other, the entire Tribo system is then developing. So it's a rather dynamic nature of the Tribo system that we encounter in sheet metal forming. So what is different to other tribology domains here is that the contact is non-recurring, that the blank and the tool only comes in contact with each other once. Then there is an area contact rather than line or point contact. And the contact pressures that we experience are in megapascals. So let's say up to 50 megapascals on average, rather than in gigapascals. So the contact is very different. And so what happens on a micro scale is I've tried to explain here. So talking from left to right. So you have only one side of the contact. So there's an aluminium oxide layer. So imagine if aluminium blank is being solution heat treated, then the oxide layer, there's an oxide layer growth that is happening. And then that layer is also porous. When the die comes in contact with the aluminium blank, which is not lubricated, then there's an exchange of lubrication. And then when there's sliding action, when the part wants to form, then there are a lot of things happening at the same time. There is breaking of the brittle aluminum oxide layer, which can lead to extrusion of base or softer aluminium alloy, which then can come in contact with the tool steel or the tool surface and get cold, when I say cold welded, but get, let's say, chemically or mechanically adhered, which is galling. And then there are some broken off abrasive particles of aluminium oxide or of the tool surface as well, because aluminium oxide is the second hardest material. So it can also wear and remove particles off the tooling surface. So an entire contact is evolving as we are forming. And at the same time, the blank is cooling and the die is gaining temperature. So again, the temperature exchange also affects the rheological properties of the lubricant, which in turn changes what is happening at the contact. And all of this is happening within less than 1 second. So I'm just now trying to make you more aware of what challenges such a contact can bring in. So the first challenge is the evolution of contact and friction. So if you look at a Strybeck curve, which we all know, divides into 3 lubrication regimes. In sheet metal forming, we have these parameters called L1 and L2, which is an extension of the current Strybeck curve, but we account for surface finish in it. So we typically only operate in boundary and mixed lubrication regime. We rarely go to heterodynamic lubrication or EHD in that regime. But what can happen with the contact that is being constantly evolved is depending on the lubricant, the type of aluminium blank, the forces and the speeds that are using, the friction can either increase or decrease during that contact. And that is a dynamic nature that is very hard to predict for some tribo systems. Then, as we keep pressing the parts, let's say we press 4,000, 5,000 in a production run, then galling, which is adhesive wear, also kicks in. Then tool wear also kicks in. So even between the number of hits and time over the production, the contact is evolving. So the friction is evolving, the contact is evolving. So then how do you then quantify a system like this? Then the other challenge is then what experiments to conduct. So if you were to look at a part being formed, then as you can see here, there are different types of contact. There is bending over tension, there is sliding, there is bending and unbending over a feature, and in the die gap there is ironing. So there are around 8 tests to characterize what is actually going to happen while forming just one part. And all of these are still, let's say, macro scale, and they don't really represent the real production conditions. So then which tests to use to then quantify what is really going to happen in a production is still a problem. Then on the right, I've just shown some research that has been done on steel, in which there are different universities and authors who have tried to replicate each other's tribology test. And what you can see here is that no 2 tribology tests in this field can be repeatable or are repeatable. So then what data to trust and what tests to trust? And the reason for that is this complex interaction of variables. This is a busy slide and a rather confusing diagram, but as I'll try and explain, is this side has all the sheet properties, that sheet surface roughness, the strength of the sheet at high temperature, and the temperature is dropping, and its hardness. And there are some tool parameters such as the coating on the tool roughness, and then the elastic deflection of the tooling. Then there are some process parameters such as the force and the relative velocity, and then there is blank and die temperature. But all these parameters are interconnected and their interaction is dynamic and wouldn't say random, but predictable, but very hard to predict. And that's one of the reasons that the experimentations are not repeatable. And hence there's a problem in how do you then evaluate a lubricant that can not only last one part, but over an entire production run of few thousand parts. So that brings me to then what should be the properties of the lubricant. So the three most important properties, which are probably common with other lubricants in other fields in tribology, is frictional behavior. So we want the friction to be predictable and constant and consistent. Then, because we are trying to lose heat, the lubricant should help us in losing more heat as rapidly as possible. So it needs to have a high friction heat transfer coefficient. And finally, the lubricant should be able to stick or adhere to not only the tool steel that is being sprayed onto, but aluminium very rapidly. And that can either happen through absorption or with some reaction elements. And all these parameters or aspects are being researched in EU and in America mostly, but UK tends to not have much research on sheet metal forming, which is one of the reasons we are trying to introduce this field to us. But more importantly, what generally is lost in research is the cleanability. There is no point in evaluating and trialing a lubricant that can be good at friction behavior, heat transfer coefficient, and does the job, but it cannot be cleaned after the part is being formed, because it gives you a lot of surface quality issues. So it's not directly linked to tribology, but Graham and I try to work on formulations which not only gives us good frictional response, but good cleanability as well. Because eventually we want clean parts to be then sent for painting. And this is one such example of that. So this is a section of a formed part, which has some remnants of the lubricant that was charred and did not get cleaned properly. And then we sent it for anodizing. And anodizing is a very rigorous process in terms of the cleaning and etching. And despite that, the lubricant was not removed. And essentially, this part was considered as a defective one. So then we had to change the lubricant, although that was one of the best performing lubricants. So these are the challenges that we face, and then we are trying to surpass. And then Graham will take you through some of the solutions. Over to you, Graham.
Right. As I was saying, I've been working in the metalworking industry, metalworking lubricants industry, for about 40 years. And like I say, I first came across this process when it was in its infancy at the University of Birmingham, probably about 10 or 12 years ago, and got involved. And then I joined in Impression Technologies about 6 years ago. And one of the issues we've always had is, because it's new, there were no industrial lubricants out there that were formulated for this process. Cold aluminium forming, there's loads of lubricants. It's been going on for donkey's years. It's there. Hot aluminium forming, forging, extrusion, again, lots of lubricants out there. The difference between these processes is in aluminium forging, you've got a warm or hot blank and a die which is maybe around 50 or 100 degrees C cooler than the blank. With cold forming, everything's at room temperature. What we've got here is a hot blank, which is in excess of 400 degrees, 450 degrees centigrade, and we've got dies that are cooled to room temperature. The production dies that we're making now are water cooled. So you've got this big temperature gradient, which you need a lubricant to survive and help you to make the part, and then you've got to get it off the part and also get it off the dies afterwards to do the die maintenance. So this will take you through some of the solutions that we've been working on. Can you, next slide please, Yogendra? Okay, so the way we go about screening lubricants and everything else is we begin with a series of lab tests where we can evaluate the lubricant performance and also its cleaning performance. And once we've done those tests, we can take measurements and pass information such as coefficient of friction back to our simulation team, who can then incorporate the information that we give them into their equations for the simulations. And one of the things that we've always said to them is that you're going to have different numbers and different results to put into different parts of the design. One coefficient of friction number is not going to make your simulation work, and that's not just true of what we do, it's true of other forming simulations as well. And once our simulation team have come up with an effective simulation, and they can show that we can make the part in, or in theory, we can make the part using computer simulation, then we go into production, we make the tools, we get the blanks made, and we follow up with monitoring of both the parts and the dies after each production run, or every other production run, depending on how long those are. So we can see what's going on with the dies and maintain them and reduce scrap. Next one, please, Yogendra. The most effective lab test that we've got running on a regular basis at the moment is that we have a small cross die tool that we use. We can make these dies from any material that we can, all the same materials that we make production dies with, and we can also coat them, PVD coat them with various coatings, and we can see the effect of those along with different lubricants. We did originally design these so that we could actually cool them, but the rate that we actually run the tests is, generally speaking, much slower than the production run would be. So the dies tend to come back to room temperature between each test anyway. On the left hand side, you've got a schematic of the tooling, with the punch at the bottom, with a blank holder plate, which we sit the blank on, and then the punch comes down from above, and we can measure the load on the press that we do this on. So we run at the same temperatures, and we can run at the same speeds as we do in production. And there's examples of some of the parts that come off that particular tool on the right hand side. We can measure depth of draw, and we can also take the load data that comes off the equipment and plot load against draw and rank lubricants that way. Next one, please. Where we get, when we don't have a particularly successful lubricant, then we start to see things like fractures and thinning. So on the right hand side there, you can see a split near the top of that part where that's fractured. With this tool being so small, we quite often see thins that wouldn't be acceptable on a production tool, but if we had a larger version of this, then we also wouldn't accept the thinning side. But given the constraints of that tool, then we accept some thinning, but not a lot. But the best lubricants, we don't see any thinning, we don't see any splits. They go to the full depth of draw, and they give us the lowest loads that we record on that information. And we can then chop these parts up and do measure the thickness of the material, as I said before, so we can then pass that information back to our simulation team. So they take that data and they generate simulation equations and run those under various speeds and loads and material thicknesses, and eventually they come out with a prediction of what we actually see in the lab, and then transmit that information along with contact pressures, blank temperatures, and so on, and coefficient of friction. A graph of which you can see on the top right, and apply that to an actual production part. And again, we can predict more accurately with this data where the thinning is going to occur, where splits might occur, where we need to apply lubricant, where we don't need to apply lubricant in some cases too, which can be just as important. Reducing the friction where you need metal flow is one thing. Increasing the friction where you don't want it to flow is often just as important. And if needs be, we go back to the OEMs or whoever we're dealing with, discuss what certain issues are that we're having, and sometimes they will agree to a slight design change, so that the part can be more easily made. Next one, please. Looking at parts that and the dies, looking at in the top right there, which is a part you can see there's a slight surface defect on there, which is sometimes referred to as orange peel. What's happened in this instance is that although there's not a lot of obvious metal movement taking place in there, what's happening is that the lubricant is pooling in that area, and having a solid lubricant component that is then acting as an insulator so that the part doesn't cool properly in the quenching operation in the cool dies, and you get this surface defect occurring. What we need to do in that case is either remove the lubricant buildup in that area, or ensure that we're not spraying lubricant in the area where it's not needed, so it doesn't migrate into there. We can also see a similar effect sometimes if we get less than optimum blanks material delivered to us. So it's not just us working on the tribology side, but we also need the guys who are doing the all the work to ensure that we've got the correct materials coming in the first place. On the dies themselves at the bottom, the one in the middle, erosion, that can be caused by either a lack of lubricant, or it can be sometimes the wrong kind of lubricant, where you can get a chemical erosion rather than physical erosion. So you get a chemical interaction between the die and the blank. Galling, which is just below there, quite often occurs on sharp radii, and has to be taken care of. And the one next to it, if we don't apply sufficient lubricant, then we can see scratching on the dies from the part moving across it, or we can also see heat spots developing because we're not using the lubricant correctly to cool the dies as well as the internal water-based cooling that goes on. Next. To monitor, another thing that we do with the dies is we monitor the surface over a period of time, and we do this by using 3D profilometry. Now, it's not the easiest thing in the world to do, to take a die which is maybe 2 meters long and 1.5 meters wide and drop it onto the bed of a 3D profilometer. So we have to do that by taking replicas at various points during the process. And as long as we're reasonably consistent in where we're taking those replicas from, then we can monitor how the galling or any other wear which is taking place on the tool surface occurs. Now, like I said, for the most part, what we see is aluminium oxide transfer onto the die surface, which is what we call galling. And the best way of removing this is with a detergent caustic solution, because that dissolves the aluminium oxide. They're like little ball bearings, but they're adhered quite strongly to the surface of the tool. And if we dissolve those with a caustic soda solution, then we get back down to the original metal and also the original surface finish of the metal. Whereas if we were to try and abrade those off, then we would be changing the surface finish of the tool itself, which could lead then to gold and coming on at a much more rapid rate. And in addition, if we've got a PVD coating on there, then we would be removing it within a few short runs and having to send the tool back for another expensive recoat. Okay, Yogendra. So in summary, using tribology, and the knowledge of lubricants and working with lubricant suppliers, and also working with tool material suppliers and PVD coaters, tribology is a key enabler, or has become a key enabler in helping us to harness the advantage of HFQ in an industrial hot forming application. Aluminium alloys themselves, high strength ones in particular, pose significant challenge in terms of the tribology and the lubrication system that develops during production. The main challenges arise due to the presence of aluminium oxide layers, which can form on the tooling, and we require relevant experimentation to develop a lubricant system. And just to cover that a little more, one of the main issues with the typical tribology test equipment that is out there is that you pretty much got to run the tool material and the blank material at the same temperature, which isn't what happens in the industrial process. So that means you got to run multiple tests at multiple temperatures and also pressures and speeds in order to try and get an overall map of what is going on in terms of coefficient of friction and other lubrication regimes that are taking place. Finally, taking this from the original academic process, we've managed to scale this up to a point where quite large production parts and real life production parts are being made, but the true reality of it is that there's still quite a lot of R&D needs doing to further promote this. The lubricants that we're typically using at the moment are graphite based, and the industry that we're selling into is not really used to using graphite based lubricants. So there's a lot of work going on to try and remove the graphite and replace it with other lubricant base, not just base fluids, but also additives to remove that solid lube. And whilst our current solutions are promising, we still need quite a bit of research to take place, not only within ITL, but also within academic research facilities, so that we can better realize the true advantages of this process. That's our little talk for today.
Okay. Do we have any quick questions? Okay, so I've got a quick one for you. It was just about the approach when obviously you're taking these large parts, and then you've got the challenge of doing the 3D profilometry. What do you actually use for taking your impressions, and how accurately can they represent the surface that you're trying to take the impression of?
So we have tried different silicon-based and non-silicon-based two-part epoxy resins, and there was because they're thixotropic, so we want the ones who are able to stay on the surface against gravity. So it's the non-silicon thixotropic ones is what we are trying to aim at.
Mhm.
And then we have done different studies in which we have found that there's this particular company that we use who make the ones that the kind of the ones we use, and then the accuracy is up to 0.01 microns.
Okay. Any more questions from the floor? If not, I think we should skip. Okay, thank you very much.
Thank you.